Yeah, so my affiliation with ISI actually is multi-generational and very familial and goes back quite some time. As you may know, ISI was originally created to do work for DARPA, the Defense Advanced Projects Research Agency. And DARPA actually needed to monitor the work that was going on in various of their contracts. And they turned to employees of the government to do that. And my father was an employee. He worked at Rome Air Development Center, which was a Air Force research lab. And he was responsible for monitoring DARPA contracts. And one of those contracts happens to be at the newly formed Information Sciences Institute. Mid to late 70s, my father would come to Los Angeles and go to the marina and monitor contracts and, of course, bring us home presents. And we would say, oh, what did you get us when you were on your trip? And many years later, when I went to graduate school in Los Angeles, my father said, oh, I know somebody who was at USC, and pointed me towards Steve Crocker, who at that time was no longer at ISI, but I ended up working for him for 8 or 9 years. Through Steve, I met my wife, who was Steve's assistant when he was at ISI. And then many years later, I was recruited to come back to USC and go to ISI. And now my wife is working there as well. So it's kind of full circle, and has spanned a period of decades as my association with ISI. So I have a very fond spot for the Institute, in addition to all the wonderful people and things I was able to do there. At one point, it was actually a decision to would I be a musician or an engineer? And I decided, well, it's probably better to be an engineer and be an avid amateur musician. So I pursued engineering, and I always found it something that I was good at and enjoyed doing. I like building things. I like figuring out how things work. I like understanding why things behave the way they do. And so for me, engineering was very appealing because it allowed me to build things. It allowed me to see stuff work. It allowed me to be creative. And I always liked applying the notion of aesthetics and design and the role that played in coming up with an engineering solution that didn't just work, but had some kind of intrinsic beauty, whether it's in simplicity or elegance in design and so on. And it turns out being a good engineer, a good computer scientist, if you have this sensitivity for elegance and functionality, and just things have to be this way because they're beautiful when they look that way, it's really very appealing. Plus you get to do something that you get to see it work. You get to see the gears turn. You get to understand how things function. And there's a great satisfaction in having this knowledge about, oh, now I understand how this works. I understand the details and the pieces. So that's what's appealing to me about engineering, and it appeals to the, very much. I also like the aesthetic side, the elegance, the simplicity, the beauty in a solution. If we look at the work that we've been doing over the past decade or so, it's really much more focused on not building technology for technology's sake, or looking at, well, how do I make this algorithm slightly better? It's looking at how is the technology interface and interact with the global, a more holistic system which involves the people and how it's used in society, right? And how that plays out, and what do those interfaces look like, and how do we complement and augment what we as a society can do? And that was one of the really intriguing and compelling things about ISI, and why I enjoy it, right, is because we look at these large-scale systems and impactful systems and have the opportunity to build things and see how they're used, and then the impact of those use. So a lot of my work is really, again, over the past decade, is focused on not sometimes what we would call the field of dreams approach, right? If you build it, they will come. But really looking at let's see what are some really important societal problems. Let's see the intersection of technology and those problems, and how we can help in a beneficial way. How do people work together? And then looking at coming up with simple, elegant, usable solutions that will then facilitate that creation of new knowledge or new systems or new tools that will overall have a beneficial effect. That's one of the reasons why ISI has been such a great place, is because it's given me the opportunity to do that. If you were in a more traditional computer science setting, right? You would be focused on small scale, let's get a paper out, let's get our students out, let's move on to the next thing. One of the things that makes ISI unique is that we build operational systems, and always done that, from the internet to the domain name service to AI systems and so on. And so it gave me a great place where I could say, I'm not going to just build something and posit that it works. I'm going to work with the best biologists or the best chemists or the best climate scientists in the world. And we are going to build technology platforms that enable them to do something important. And we can study as to whether what we've done is effective or not, based on whether people can use it. And so ISI has been a great place to do that, because we can look at these larger scale, holistic approaches to the role of technology in society. I joined ISI, I guess, in 1997, 98. I had spent the previous 7 or 8 years at Caltech in the computer science department in the Beckman Institute, and had started poking on some of the ideas about high-performance computing and network-based computing, looking at the transition as the internet was really becoming broad-based. I'd done a lot of work with high-performance computing or supercomputers, and realized that I wanted to do something bigger associated with really building and fielding large-scale, global-scale systems and looking at how they were used. And so I was recruited to come to ISI by Herb Shore, who was the 2 directors ago of the Institute. I came in from the world of high-performance computing, but I think it's kind of interesting to know people talk about high-performance computers not as high-performance computers, but as time machines, right? And that what a high-performance computer, and what we were doing in that time, which was, again, kind of early 2000s, was exploring what would it mean if we had orders of magnitude, like multiple hundreds or thousands of times more computing than we currently had on a PC, like a desktop machine, like a Mac II might have been around at that point in time, or an IBM PC. What would it mean if we had 1,000 times more computing and 1,000 times faster networking? And so supercomputers kind of gave you that hint as to what the world would look like. And so it was really the question of, well, the networking people had thought about networks as communication means, and we had, of course, email had become more developed at that point in time. And we could, early on, there were ways of moving large-scale files around. Things like Gopher and FTP were widely established. At that point in time, Tim Berners-Lee had been pushing on the World Wide Web, which came out of CERN, which was the high-energy physics lab in Europe, that at the time was working on developing the next generation particle accelerator to discover this particle called the Higgs boson. They wanted to look for that. And so there was this multi-year, multi-decade activity to upgrade the accelerator at CERN and to explore whether they could discover this particle. So these ideas had been kicking around. Well, we could use this network. We could maybe get remote computers. We had time-sharing operating systems. We had the World Wide Web. And we asked the question, well, if we have all these things, what does that fundamentally change in the equation? And what if we could not just remotely access a computer, but what if we could really share it in a very profound way? So me and my close colleagues, Ian Foster and Steve Tiki and these groups of people I were working with started building systems and saying, well, what could we use them for? What are some of these profound problems that we could apply them to? And at the time, back then, by luck, because I was working with my colleague Ian Foster, who was associated with Argonne National Laboratories, which was the Department of Energy, and I was at Caltech at the time, we fell in with the people building the next software systems for discovering the Higgs boson at CERN. And so we got involved in how does one build a global computing platform for solving the grand challenge problem in physics, which is, does the Higgs boson exist, the so-called God particle? Does it exist? And so we played a very integral role in building the computing platform for analyzing the huge amounts of data, which were huge at the time, coming off of the brand new Large Hadron Collider at CERN to figure out if the Higgs boson was there. And they adopted this approach. And the Higgs was discovered on a global computing platform with resources and data shared all across the world. And people were building national scale platforms for doing shared computing based on the approach and the technology that we had developed at ISI along with my collaborators. And lo and behold, the Higgs was discovered. And the Director General of CERN said this would not have been discovered without this grid computing platform, that was pioneered, that we had the opportunity to create. And so that was, very satisfying. Now, of course, I don't have a Nobel Prize in my office, but the discovery of the Higgs took place on this grid computing platform. We played also through the Department of Energy a very influential role in doing some of the data and management analysis that was associated with some of the large-scale Department of Energy climate models that went into the Al Gore's Nobel Peace Prize. We built something called the Earth Systems Grid, which was moving around large and managing large amounts of climate data. And the LIGO Gravity Wave Observatory was also built on a grid platform, or had elements of a grid platform in it. I realized we had been working primarily with these large-scale, very organized, well-funded global initiatives, and the realization, like the Higgs boson, but the recognition that while those were important, that's not where most innovation takes place. Most innovation takes place in smaller scale, small teams, individuals, and multidisciplinary collaborative activities, not focused. I'm going to discover the next particle, prove whether the Higgs boson exists. But these more ad hoc, dynamic, multidisciplinary collaborations. Our work turned more towards looking at what are the dynamics of these small groups and what's the nature of organization and communication within those small groups. Early on in our initial work with grid computing, we created the notion of what we called virtual organization. So very, very early on, we were interested in the organizational and social structure for collaboration that was enabled by resource sharing at a distance. And so we did a lot of work in that area. And then kind of the interest turned towards, those are big IBM-style organizations, top-down, lots of policy, lots of money, lots of structure, right? How does that now look more like Silicon Valley now? Bottom-up, innovation, very agile, very small. So how do these virtual organizational techniques apply there? So we turn towards these more chaotic, what sometimes are called long tails. So, right, that 90% of the science is done, or innovation is done in these small groups, and only 10% is done in these large groups. And so how do you address the needs of these, the bulk of where innovation happens, right? And the nature of them, where they can't afford, it's not IBM, right? It's more dynamic. It looks more like an art studio, right, than a production line. And so how do you enable those creative processes? So that turned us to look towards smaller scale collaborations, and also turned from natural sciences to biology, where the knowledge is much more unstructured, the processes are a little more chaotic, and there's lots of different types of measurements and activities happening. So over the last 10 years or so, I've been looking in biomedical sciences and in those types of collaborations. And so that's been very interesting. We've learned a lot of new things. I get to spend a lot of time working with microscopes and sequencers and X-ray sources and so on. So that's been very interesting and intriguing. The last decade or so, we've been focusing on biomedical research in our research area. And the initial problem that we looked at tackling was that so much of biology now is not about looking at things in test tubes, but it's about collecting and analyzing data. And so it kind of occurred to me that so much of modern biology is actually focused on the skill sets and the expertise that we have. And so what we've really been looking at is how do we turn the management and analysis of data from being something that's ad hoc to part of the science. And so that's really been where we've been contributing. It's really interesting. As a computer scientist, we think we're surrounded by data, and everything is data. And the spreadsheet is data, and the program is data, and the results of the spreadsheet are data. It's all data. And one of the interesting things I discovered was the social aspect of that, and the difference of culture and the importance of language, and the role of culture and language in the work that we do as computer scientists and technologists. So as a computer scientist, I look around and I'm surrounded by data. Everything is data. It's all stored on a computer. It all has properties. We all want to take care of it and manage it in effective and disciplined ways. And I was quite surprised when I had conversations with biologists, and I say, show me your data. And they would say, oh, I don't have any data. I said, well, what do you mean? You have the spreadsheet, you have the simulation, you have this program that you ran to compute your p-values to determine whether you got the right answer or not. Isn't that all data? I said, no. Data is what came off the microscope, or data is what came off of when I made the measurement out of this test tube. I don't have any data. I have my data over there. All this other stuff is not data. So that was really interesting to me and made me realize, part of what we're doing is educating and training and making them realize that all this computing stuff, which is now so integral to doing biomedical research, is part of the science. It's part of the experiment. And so part of what we've been trying to do is to instill this knowledge that the computing part is just as important as the mouse that you make the measurement from, or the X-ray, or the MRI. And we need to treat it all effectively. And we look at what's the great societal problem we face. Well, recent studies have come up that show that only 20% of the papers published in leading journals in cancer research are reproducible. That means 80% of our time and effort and investment is on results that we can't use. And from a societal perspective, this is terrible, right? This is really bad. This, as a taxpayer, it means I'm wasting 80% of my investment. As a scientist, it means I'm wasting 80% of my time. And as a patient or a society, I could be getting this tremendous benefit that I'm not getting. So the big problem we're looking at is, how do we go after making that 80% smaller? Now, certainly that 80% is not just due to computing and data. There's lots of reasons why an experiment can't be reproduced. But certainly what we discover is that the management and thinking about what is data for my experiment plays an important role in our ability to reproduce either positive results or negative results. So the work that we've been doing is really focused on how do we make sure that the scientists in these small dynamic multidisciplinary groups are as effective and efficient as possible, that they don't do the same experiments again, that they keep track of what worked and what didn't work, right? And that they do the best job possible of creating results that other scientists can pick up and reproduce. So we make that 80% number as small as possible. So that's the problem, the big problem we're going after, right? And we achieve that by thinking about what's called, in my area, social technical systems. We're not concerned about the technology. We're not concerned about just the people, but we're concerned about how the technology and the people mesh together to be more effective and more efficient and communicate better and understand better. So we actually look at these social technical systems in a very broad setting. So ideally, it's how do scientists of different areas of expertise communicate with each other so that they can create and share knowledge? How do we train scientists so they understand how to communicate with each other? How do we more effectively create scientific results that are transparent and reproducible so we know that they're correct? And then ultimately, how do we take those results and translate them to a broader community, whether that's for STEM, diversity, or just the general public, so they understand and trust the results because they can see how they were there and they can translate that into language that they can understand. it's important that you document failure, because if you don't record your failures, you don't learn from them. What we do is we don't say censor your result. In fact, what we have been pushing in our work is say, let's make it so easy to record everything. You just keep track of all of your data, good, bad, or indifferent. Don't edit yourself. And then when you're done, you say, these are the things that worked. These are the things that didn't work. Person who wants to reproduce my results, you see everything. Okay, the picture was out of focus, right? It's fine, here it is out of focus, right? And so it gives you the opportunity to learn from failure. You know, if we could make an analogy to making a documentary like this, right? All things being equal, you'll keep all the outcuts. You'll keep everything. You'll edit down a final version that will become the documentary, right? But assuming the costs of storage are not too large, you'll keep everything else, because you never know whether you might need it, whether there's some good stuff, whether, you know, it might be useful. And we need to do the same thing for science. We have examples where by recording the failures of our experiments, we were able to detect mistakes in our procedure that we went back and we fixed. So how do you build a platform that encourages failure in a flexible way? And so one of the things that we look at when we build these social technical systems is we look at what are the types of organizations that we want to support. And if we look at, say, enterprise information technologies as an example, we can see there's two extremes. If you work for an insurance company or a bank, you have what's called a business process management system. And these are rigorous systems that have, because you have practices and policies that have been written down and legal requirements where you follow well-prescribed workflows. You do this, you do that, then you get 3 signatures, then you do that, then you fill out this form, then the following things happen, right? So that's one class of systems. And to be honest, in the science domain, we've often tended to do that. The focus is on the process, and we document the process and we write it down, and that's what we want to record. And historically, that's what we look at. On the other side of the coin, there are the so-called creatives, people who make movies, people who manage photographs. And if you look at the software and the environments they have, they're radically different. They're about free-form exploration around the content. So they focus on what we call content management systems. So you look at things like photo applications, right? Apple Photo or Google Photo or so on, right? They're not about process, they're about content management in a creative and free-form way. And if you think about what are the things that I do in a photo app or the editing software you'll use for this documentary, right? You'll collect all your assets, you'll make rough cuts, you'll create albums or edits, you'll share those rough cuts or albums with your colleagues, you'll iterate on that, you'll keep all the old versions, finally you'll say, this is the one I want to share for this purpose, right? You'll publish that, you'll go back, you'll do another edit, you'll do a short version, right? So it's all around free-form interaction with the content in a creative setting. So, and that's the social technical environment that supports. Radically different than what a bank would do, right? You don't want to be creative in a bank. Again, there's variance, right? If you're doing a clinical trial, you don't want to be creative, right? Those are well-defined process. You must do step A, B, C, and D. If you want to discover something new, it's creative. So we build systems that look at social technical environments or ecosystems that support creativity. And part of that is recording your failures, your successes, publishing lots of versions, managing lots of versions, focusing on the data that you want to share, less so than the process that you use to create it. In some sense, our work achieves two things. One is, of course, we provide some incremental achievements, but the other, more important, is that we provide fundamentally new ways of doing science. And ultimately, the work we're looking at is how do we transform the methods of science. Our end goal is change the basic paradigm of science. And if we look at, actually, a very famous computer scientist, Jim Gray, talked about the scientific paradigms, where we started with an experimental paradigm, then we learned how to build formulas, and then we had simulation, and then we went to this kind of data simulation-based paradigms. So what we're looking at is a fundamental transformation in the paradigms of science based around these kind of data sharing, data-centric science, we call it. So that's our end goal, is just to fundamentally create new paradigms for doing science around data-centric, this notion of data sharing, data is the primary artifact. If you look at the work we've done, I could point kind of two things we've done which have been kind of fundamental transformative characteristics, results, which I would like to think that would not have been possible without our contribution. So one is, if we go back to the discovery of the Higgs boson, they simply did the computing platform to do the analysis required to discover the Higgs simply did not exist. And the creation of grid technology and our engagement created a global computing platform that previously simply did not exist, that allowed them to do the analysis for the data coming off the accelerator. That would have not have been possible. And now, of course, this is much more commonplace with the emergence of cloud computing and Amazon Web Services and things like that. We now have this is now commonplace, but back when we did this simply didn't exist. And this discovery wouldn't have been possible without this approach. The other thing that we've done, which has been transformative and fundamental, is something I've been more intimately involved with, which is some work we've done here at USC, which has been looking at a multidisciplinary collaboration with some neuroscientists, microscopists, and in my group, looking at a seemingly quite difficult question, which is, how is memory stored in the brain? And so as you may know, the brain is composed of neurons, and neurons have these connections. And these connections are basically enabled or disabled by the creation of these things called synapses. So synapses allow electrical signals to jump from one neuron to another. And that's been long-standing theory that memories are formed by changing the strength of these synapses in the brain. Now, it's been possible to look at these, and the way you do that is you basically kill the subject that has the brain you're interested in, and then you can use things like electron microscopes to go and look for the formation of the synapses. Well, we had a collaboration here where we had kind of three things. We had one is where we said, well, we have a way of genetically modifying an organism, in this case a zebrafish, which you can go to an aquarium and buy, but turns out to be a very common model, what's called a model organism, that's used to study basic brain function. Turns out there's enough commonality between a zebrafish brain and a human brain to be interesting. And they have the advantage you can see through them. We had one of our collaborators said, well, I have a technique where I can genetically modify the fish so that whenever one of these synapses is formed, I can put a little phosphorescent marker on there so that if you shine the appropriate laser light on it, it will glow green. And then we had another collaborator of mine who said, well, I can build a microscope where I can look in 3 dimensions and shine very fine degrees of laser lights on a brain in a fish and make them glow green and image them. And then my group said, well, we can then take those kind of pictures of these glowing green bits and turn them into maps of where we think synapses are and aren't. And then we had a person, actually also a neurobiologist, who said, and I can figure out a way to train the fish to be afraid, that using classical light aversion training, train the fish to know that when a light comes on, they're going to get zapped in the nose with a laser, and they don't like that. And we can measure the extent that they don't like this. So we had this remarkable thing where we had the ability to take a little baby fish, a couple days old, modify its genes so the brain glows green when there's synapses, train it to be annoyed that it's going to think it's going to be hit in the nose with a laser, and measure what happens to the brain. So we went through many years of trial and error, things work, things not work, till we actually came up with a paradigm where we could measure the brain of the fish before, train the fish to be concerned if a light turned on, that they were going to get zapped with a laser, and measure the brain after. And then, lo and behold, we discovered something quite remarkable, which is that the fish learned not by changing the strength of the individual synapses that were already in the brain, as people traditionally thought, but that synapses of one part of the brain basically went away, and synapses were created in a different part of the brain. So we saw that the locus of the synapses actually changed position, which is a fundamental new result. People didn't know that. And we could do that because we are the only people on the face of the earth right now who can measure the location and change in synapses in a living organism. And so this is really an important result, because this is a bit hand-wavy, but why do certain types of human conditions like PTSD, why are they so hard to reverse? Well, maybe it's because it's not a little minor change in the brain. Maybe it's because we've got these major structural shifts in the way the brain is recorded. Now, one of the things that's really interesting about this is because we followed this paradigm where we recorded every single piece of data, good, bad, or indifferent, from day one of this experiment, and it's all available and documented as part of our daily practice, right? That when we publish the paper in the Proceedings of the National Academy of Sciences, rather than having a picture that has a couple of dots in it that says, here's our result, isn't it pretty? Believe me, you were actually able to click on that picture and go back and see every single piece of data that went an analysis that went into that picture, all the way back to the details of the microscope from which that data was collected and the raw images that came off of that microscope. So anyone who wanted to go and redo our results had the ability to look at every single piece of data that we produce. So this is really fundamental. It demonstrates we used a fundamental new mechanism for doing science, a fundamental new methodology that had unprecedented reproducibility and transparency, that's coupled to our publication, that created a fundamental new result in neuroscience. And this is just kind of a wonderful story, and the kind of thing you could only do in an organization like ISI in a place like USC. So the result of our new techniques and our experiments is we were able to essentially map where in the brain memories are formed. So nobody else has been able to do this before. It's a wonderful experience to say, I am seeing something that nobody has seen before and nobody else can see. And so that was really fantastic. And to look there and say, we think this is what's happening, and here's our result. Yes, we're right. We really can see here's where these memories now live in the brain, and they weren't there before. One should be careful not to generalize too much from what we see in a zebrafish, but there are hints that a lot of some of the more difficult to overcome human conditions like post-traumatic stress syndrome are so hard to cure because, by analogy, if we're literally changing the structure of the brain rather than just making these minor changes, that's why it's so hard to back these things out. Because we have to now take these new regions that have been formed and destroy them. Not destroy them, but make them go away and move them back to where they were before. Not just change them a little bit, but change them a lot. And so, of course, we're a long way from being able to say that, but this gives hints as to why these types of syndromes are so hard to cure. So much of the transitions in science were built around the creation and use of new instruments and new forms of measurement. And so our ability to understand electricity or the structure of the atom or radioactivity was we built new instruments that allowed us to measure these things. And those resulted in new scientific methodology. Our end goal in the work we're doing in the future is we'd like to fundamentally change the way we do science so that the operations and sharing of data becomes a core part of the mechanism, a core part of the training, a core part of our instrument, So that's really what we're after. So if we're successful, right, just the way we think about doing experiments and doing science will be fundamentally different. And as part of that, because we're looking broadly at these mechanisms of exposure, transparency, and communication, ideally we would like the ability to translate those results and have them understood by the general public and society at large will also be enhanced. So really what we're looking at is making science more efficient, enabling fundamentally new types of discovery that will be enabled by all of these advances in things like machine learning and AI and all these new instruments that are being developed, right? And to translate those results. So much of what we hear about, and it's easy to fall into, everyone's very excited about things like machine learning. Well, we need to realize that in science in many areas, we have this saying, garbage in, garbage out. So the ability to create a wonderful new algorithm for machine learning or vision understanding or a new instrument, right, doesn't achieve anything if the data that comes in is meaningless, and if we don't properly interpret the data that comes out, and we don't effectively and accurately expand and exchange those results with our fellow scientists and the general public. So in some sense, it's a little bit less sexy than saying, oh, I've developed this new algorithm that could automatically, figure out what pizza you want to order. But if we don't look more carefully at what went in and what went out, and am I really comparing something? And did the data that go in, does that really represent the right thing? Then all these advances we're making in other areas are meaningless and in fact dangerous, because it allows us to make decisions and predictions and actions on meaningless results. And we only know whether we've done the right thing if we carefully document the process we went in through, the data that came in, the stuff that didn't work, the pieces we threw out because we didn't think they were important. And only if we have that, if we integrate those as our fundamental mechanisms for doing innovation to discovery, should we and can we trust the results, and should we make decisions based on those results? So that's the big picture. Let's not have wonderful algorithms that produce bad or harmful results because we didn't carefully consider the inputs and the outputs and how those were managed in creating those results.